In a way, we're really starting the theory. We've developed vector bundles. Of course, you have to do characteristic classes. And now we've got this way that we're going to produce these characteristic classes through manifolds mapping. Let's just set the stage again. So what I want is I'm going to consider just vector bundles over manifolds. And maybe this is going to be just to set notation. I'm going to think about the fiber as just call it V, which is going to be rank n, Rn. Again, this is not necessarily compact, but we do want no boundary. And then what we just to touch base and say yes, we've got a satisfactory general theory by doing this. What you can do is M equals, for example, a neighborhood of some finite complex in Rn, in particular any simplicial complex, which can be embedded, any finite simplicial complex can be embedded in a delta n-1. And so then if I just take the neighborhood, so just think of the one skeleton of the tetrahedron and take some tubes around it, that's a perfectly good neighborhood, and that deformation retracts onto X. So we're capturing all these finite homotopy types by doing this. We've shown that homotopic bundles, homotopic maps induce isomorphic bundles, so we can transport the vector bundle theory from X to M. Okay, so we're going to be working smoothly. Let's then remember that I can just scalar multiply down to 0 provides a way to deformation retract E onto, let me call that map Z, the 0 section of M, okay? And then the thing to remember is that if M is a manifold, then E is a manifold. And E comes with this amazing submanifold, namely Z of M is a submanifold. In fact, the normal bundle to Z of M is E. I should have given you that as a little exercise in the normal bundle. So any bundle occurs as a normal bundle because to a manifold, if it's of course, it's got to be a bundle over a manifold base to begin with, because that bundle is the normal bundle to the 0 section. So that's the setup. I've got this canonical manifold inside of E, and then let's now make a definition which relies on the machinery we just developed. I'm going to call the Euler class of E to be the cohomology class represented by this 0 section. So the tome cochain associated with the 0 section. That gives me a cohomology class in E with R coefficients. We'll talk about what cases for R. But then, as I just said, E and M are homotopy equivalent. So that's, of course, in the cohomology of M as well. And let me just say the dimension. Well, the dimension of a cohomology class is the codimension. V was rank n, so this is in Hn. This definition can be made for all E. So for all E, choose R equals Z mod 2. And you've got a definition. We don't need to talk about orientations. But otherwise, in general, And in particular, when R is Z, we get this definition for Z coefficients when E is oriented. Because then, again, Zm, its normal bundle is E, therefore Zm is co-oriented, and the definition works. Okay, so that's the Euler class. Let's recap. Any vector bundle over a manifold has a submanifold I can name right away, the zero section of the manifold, and that defines the Euler class. End of story. Well, not end of story, but very clean beginning of story, I guess we can say. To get a class in the cohomology of M, I'll drop the coefficients for now. What you can do is you can pull back through any, this this cohomology class through any F from M to E, which is a homotopy equivalence. Well, that's just true. If we want a tome cochain representative, we have that F must be transversal to Z. So in particular, I mean, one F you could use a priori is Z, right? Z, the zero section maps back and is a homotopy equivalence. So at the cohomology level, that's fine. So let me just say, so e.g. F equals Z. At the cohomology level, that's fine, but we want F to be transverse to Z. So typically, you take it to be a section. Then what do you find? Well, for example, let the dimension of M be the rank of E, which is N. Then you would find that the Z of M is codimension N. Therefore, sigma inverse of Z of M is just going to be, well, the zeros is going to be the discrete set of zeros. Then all you're doing for, now if M is a closed, say, oriented manifold, and E is also oriented, a key case is E, the tangent bundle, then HNM is Z, and the way in tome cochain language that we talk about it is it's generated by, say, a single point. More generally, any cohomology class is represented as a tome cochain by some finite collection of points. In this case, the preimage of the zero section is such a finite collection of points, and where you say it into Z is just counting those points. So the cohomology class, so the Euler class, is an integer in Z, which is HM, is given by the number of zeros. So that's what we discussed before. So But more generally, you don't have to have the rank n is the same as the dimension. So, or more generally, the way you would say this classically is that the Euler class is Poincare dual to the zero locus of our generic section, sigma. So that's the Euler class. But again, we, instead of saying Poincare dual, we use this Tomko chain language. Great. The other way to then talk about that, just to, again, kind of button things up and connect, suppose I've got x in some other degree in the homology of M, any such is represented by some P mapping to M, and P is just a complex, which is a pseudo-manifold. That's why I called it P. So, so then we've got, I'll use F here now. We've got a fundamental class in the top homology of P. P is a I-dimensional simplicial complex. And what we mean by represented is just that the image in homology of that fundamental class is the class we want. You can always have such a pseudo-manifold because I can take the simplices that determine a cycle representative. I want to say smooth for things that we're going to do in a moment, and I can glue them starting sort of pair by pair, because in the definition of the cycle, the faces have to match up exactly to in M. They have to cancel, and so I can use that cancellation to just say, well, let's identify those faces. There's not a canonical way to do that, but you can always do that. So then, and in particular, like maybe we think of M as being smoothly triangulated, in which case P can often be just the subcomplex. So then what we can say is that the Euler class of E evaluated on the homology class X is equal to this count of zeros of a good section, transverse section of the pullback of E. So so that sort of buttons up some of that connects with the ideas we had before for this these Euler counts. These Euler counts are now cohomology classes represented by this this tome space. These tome cochains. We're at tome spaces next. Okay, so what next? Because we already did some Euler class exercises. I think I'm done with them for now. I'm ready for the next thing. Hope you are too. There's a couple ways to proceed, but in the end, as Milner showed and Stasheff dutifully recorded, there's one way in particular, one kind of development that really does great from both axiomatics and calculations. And we're going to sort of follow the development of the Stiefel-Whitney classes. As we'll say at some other points, that's not the only way. I mean, any homology or cohomology, they're just modules, and that means that there can be many interesting bases, but by far the best approach from a lot of perspectives is to do Stiefel-Whitney classes. An alternative point of view, as we'll discuss a couple of weeks on, is we can think about these more from a Schubert perspective as well. So if we want to generalize, let's turn this. So, Zm meant that the vector in the fiber was 0. But another way to say that is that the set consisting of that vector is dependent. And again, in terms of this philosophy of identifying submanifolds of the vector bundle itself, Zm being such, it's important, if I want a submanifold of the vector bundle, to say something that's kind of coordinate free. So there are submanifolds potentially. If I have a non-zero section, I could look at its span, so I could or something like that. But or if I had full coordinates, there's lots of submanifolds I can define. Just take my favorite submanifold of Rn and jostle it around, translate it around. But the whole point is that we're not allowed to do that. Vector bundles twist, coordinates only exist locally. And so, but another thing to say, so next, let's consider V and W two sections which are dependent, because that's also something that we can say coordinate free. So you would try to define a subspace. Well, you can define a subspace of E plus E. I'm going to call it D2. Oops. For the second dependent set, so Z of M is going to be our D1. The first dependent set. The second dependent set is going to be the set where, well, V and W are V plus W, such that V and W is a dependent set. Unfortunately, this is going to not be smooth. So let's remember that for our tome cochains, we're using pullback. We want submanifolds, Stokes theorem, everything depends on smoothness. And this is not smooth at 0. We'll come back to how it's not, but we'll see it presented as a quotient of something smooth in a second. So since it is naturally some sort of quotient, I'm going to put a hat on this for now. It's D2, which has been pinched together. And yeah, and so we're going to have to work to actually make something nice and sensible and smooth that does the job of this D2. Okay, so it's time for a digression, so to speak. I'm going to start up here. There we go. Let me actually move over a bit. Okay, so here's this digression, which is not a digression at all. You have to do this at some point when you're doing characteristic classes. We're trying, by the way, to get a relatively early definition of characteristic classes. What we're going to do fairly soon is see that from their properties, which we won't establish right away, there's so many wonderful calculations you can make. But Milner and Stasheff present those properties, and then you do all this work and eventually establish existence. We're going to do something similar, but get around to the existence much more quickly in the story. But part of that story is always the following characters. So I'm going to, and this is going to be slightly different notation from Milner and Stasheff, STKV. This is going to be a Stiefel manifold. And all it is going to be, let's call it K frames or K linearly independent things inside of a direct sum of K copies of V. So this is just some open submanifold. Generically, well, if K is less than the dimension of V, if it's, I guess, empty if K is greater than the dimension of V. Okay, so that's, it's kind of like the configuration space from last time. You've got this Euclidean space and you're cutting some stuff out. In the configuration space, it was linear. This is actually, yeah, this is kind of cutting out some curved things. If you think about the equations for linear dependence as it's maybe quadratic, or anyways, I should know that, but I don't recall it off the top of my head. And then define GRKV, the Grassmanian. So this is, ST is Stiefel, and this is Grassmann. So what is this? It's going to be the Stiefel manifold in V modulo. There's going to be an action on the Stiefel manifold GLKR. What is that action? Well, let me just give you an EG. If I have a frame of two vectors, say V1, V2 are my two vectors in V plus V, and I want to act by the matrix 1, 1, 0, 1, well, it should be pretty clear now. I'm going to take V1 plus V2 and then V2, say. This is something that happens within V. It's, so you have to be careful, because here's the way you want to say it. Well, these K linear independent things define a subspace, and it's rank K, and GLK can act on that subspace, but it's got to act through, usually, if you want to say matrices, through a basis. So this is just to be clear. We can act without actually choosing a basis. I guess you could just show that any choice of basis, this would be independent, but I prefer to just point out this action. And well, but then any two sets of K frames which are independent are going to be related by some element of GLKR. So this is called the Grassmannian, and the equivalence classes are in one-to-one correspondence with K-dimensional subspaces of V. And typically what you say is the Grassmannian is the space of K-dimensional subspaces of V, but it's not entirely obvious how you topologize. So the easier thing to do is take the Stiefel manifold that's obviously topologized as a subspace, and now use the quotient topology for this action of GLKR. I'm going to say exercise, although I'll do part of the exercise because this is important for us. And this exercise is covered in Milner and Stasheff. So show that GRKV is a manifold of dimension k times the dimension of V minus k. So this is lemma 5.1 in Milner and Stasheff. I'll go ahead and just say that. What's the idea? Because we'll need this idea in a moment as well. And then, yeah, the exercise is maybe to write a couple things down given this idea. So I've got X in the Grassmanian of K dimensional subspaces of V. My picture is that maybe X is here, right? It's just some linear subspace. And the point is that a neighborhood of X is going to be subspaces Y, which are graphs of linear maps from X to X perp. So the point is that here's X perp going through the origin, and that we get a neighborhood of at least nearby. In fact, it's pretty big, actually, this neighborhood. Basically, if you avoid X perp, if you just intersect X perp in a single point, which is a lot, then this neighborhood will work. But in any case, I can think of that Y as a graph of a function. You know, in this case, if I make X the x-axis, it's some linear function with small slope. But in general, I claim that that there's a one-to-one correspondence between these Y, which only intersect X perp in a point, and the graphs of linear maps from X to X perp. But that is, once I use bases, again, and I'm not in a vector bundle here, so I'm free to use bases. I'm just topologizing Grassmanian. I'm not doing something in fibers, although I will do that in a second. So I'm free to use bases, and so that's isomorphic to matrices of rank n, which is K, which is the input, the linear map from X to X perp. The dimension of X is K, and the dimension of X perp is the dimension of V minus K. So, okay. So that's one key character, is this Grassmanian. And you're inevitably led to Grassmanians when you study vector bundles, because they have some of the most wonderful vector bundles in the universe. They're sometimes called universal. That's true in the limit, in a sense. But then they're the more standard name for all Grassmanians are the tautological vector bundle. And they're just subbundles. And sometimes they're called canonical as well. Although then, you know, various other subfields have their canonical bundles in various settings. So I like tautological for the following reason. What are they? Well, their notation is going to be gamma k v, because I'm doing Grassmanians of k planes in v. It's going to be a vector bundle over gr k v, which is going to be a subbundle of the trivial bundle. So this is going to be tame by construction. And all it is, it's a joke, is the space of pairs where X is in the Grassmanian That's what I meant by putting it on the first coordinate, and v is an x. And that second one seems like a joke, but it works. So you've got a subspace and just some choice of vector in that subspace. That's all. Let me give you a little exercise. Show that gamma 1 R2 is the Mobius bundle. This pleased my daughter this morning, who's named her beta fish Mobius, that I was doing more with the Mobius bundle. So we would of course want to check that this is a vector bundle. For the trivializations, well, we would want identifications of the fibers, which are, each fiber is the point in the Grassmanian. So the fibers are the subspaces X. So on one hand, downstairs X is a point. In this tautological bundle, X is a subspace, right? And you have to get used to, again, it's tautological because I've got a space of objects, each of which represents a space of points, each of which represents a subspace, and the bundle is to take the subspace. And I want some sort of trivialization, but the nice thing is these trivializations are exactly given by this same story here, the neighborhoods that we use for manifold structure. Also then, because this linear map from x to x perp, from x to y, sorry, from x to x perp, then gives an identification of the subspace y with this graph. Well, that from the map, the linear map, it's not the map from x to x perp, but the linear map from x to the graph of that map, which is y, then gives us a way to identify x and y, which over all of these will be consistently a trivialization. You know, in other words, if I had a basis for x, I could use these linear maps to impose a basis everywhere else, and that's a trivialization. So yeah, you can say exercise, write down some of that as well, but if you find it convincing, we can go on. Okay. Let us also, let's add one more piece of data. I'm gonna define a map P sub V for the projection onto V of the Grassmanian. So let me make sure. Yes, I want it from, sorry, from the tautological bundle as a sub-bundle of the trivial bundle. I do have the projection onto the Grassmanian. That's a vector bundle map. This isn't a vector bundle map, but it is something that that says, okay, I've got a subspace and then a point in that subspace, and so I can just forget about what subspace I'm in and remember that point. Generally, this is going to be what if you well, let me give that as an exercise. It's fun to think about. So what are the fibers? So PV is surjective. What are the fibers pre-images of points in V under PV? That's kind of a fun thing to think about. So we have that data. now I'm going to define, we have all the characters we need. So definition, let's continue what we were trying to do above. I'm going to define D2E to be, I'm going to take the direct sum gamma 2E plus gamma 2E. So one more exercise. Define both GRKE. Well, you can do it all, but the ones we need are then especially gamma K E. Okay. The Grassmanian was this linear subspaces of V. Again, linear subspaces don't really care about coordinates. So under the transition functions, they would map to each other. So I can talk about the Grassmanian of k-dimensional subspaces of E now, and also this tautological bundle, which would be a bundle over the Grassmanian, and then a bundle over the original base 2. And in fact, and then an element of gamma 2 of E. So what is the base of gamma K of E is a Grassmanian. The direct sum then of gamma K with itself means I've got a k-dimensional subspace, and then I claim just 2 points in it, right? So I'll let you ponder that, but it's not 2 subspaces. This is the internal direct sum. It would be 2 subspaces if I took the bundle over GR2 plus GR2, but I want the internal direct sum. So let me just say that in another color, not the external direct sum. So now I've got, this is really the bundle who is a 2-dimensional subspace of E and 2 points on that. And what I can do is I can use this PE map to get the 2 points in E back. And the claim is that sort of generically, this is going to be a one-to-one map, because if I have a 2-dimensional subspace of E and 2 points on E, and I remember those 2 points, then usually taking their span will tell me that 2-dimensional subspace, but not always, in particular when there's 0. And that's where the D2 hat had trouble. And so, yeah, but our D2 of E is going to be this space. And what we can do is we can call this the space of, well, so again, it's a 2-dimensional subspace. I really need, in this case, sorry, it's 2 points, but it's 1-dimensional. Everything works. Right. This is still going to be an embedding, right? And in general, it will be what I will project onto is the space of linearly dependent collections of 2 points. So by construction, let me say that down here. Sorry, I didn't. So what is a space of a one-dimensional subspace and 2 points on it. And then you're just remembering those 2 points. Well, those 2 points which are on a one-dimensional subspace, then what we have is that those must be dependent of 2 points in. And for any dependent collection of V and W, there's at least, because in V and W, one is a scalar multiple of each other, basic linear algebra. That means that there's just a line containing both of them, right? And so this is surjective. So first of all, it maps to the dependent collections of V and W and E plus E, but it is also surjective. And it is this, so this is an isomorphism onto that image. So the image, so the claim is that, so this is the image of PE plus PE, and then the next claim is that it's an isomorphism most places. Claim that PE plus PE is 1-to-1 on all but well, exercise to figure that out. But then, well, here's a hint that, well, I'll pretty much then give it to you on all but when both points are 0, on all but the preimage of 0, 0. Of 0, 0. Again, that's an E plus E. In that case, the preimage is just a copy of GR1E. There's just some line that 0, 0 was sampled from. I just don't know which. So if I sample almost any 2 pairs of vectors which are dependent, if one of them is non-zero, then I know what line they were sampled from, namely the span of that. But if both are 0, if I chose 0 for both of my points, I don't know what line it is, and that's GR1E. And by the way, I meant to say, let me give one more exercise, because back in sort of some basics, GR1V is isomorphic to the projective space on V, which would be isomorphic to RP dim V minus 1. And here's a little exercise that's isomorphic to GRn minus 1 V if V is rank n. And in general, GRK V is, we can find a nice, beautiful homeomorphism between GRK and GRn minus K. So in this case, I've got D2 is the this space that wants to be the space of dependent collections of V and W, right? So the claim is, let me write it up here now. That this factors through D2 hat, which remember was that subspace. And so D2 is actually something that's smooth because it's a vector bundle over a Grassmanian, which is smooth. The Grassmanian itself is this Grassmanian in a vector bundle. So we're already getting more complicated. I guess there's some necessity to that. Again, I want you to say though that this is again a homeomorphism. I want you to see that this is a homeomorphism, except over, in this case, over 0. And we'll talk about we'll generalize this next time. Let me wrap this up though by just saying, we'll end with the definition that we want, and we're gonna proceed and make this definition more general. So we're going to give it, first let's give an alternate name. This is all with mod 2 coefficients. We don't then have to worry about orientations or really co-orientations. So let's let W in, and again here, let's remind ourselves that we've got V to E over M, and this is rank in. W in of E is going to be the mod 2 reduction, or I mean, if the Euler class was mod 2 to begin with, the Euler class of E, and that's represented by D1 mapping to E. And then Wn minus 1 of E is going to be represented by what we just defined, this D2E mapping to E plus E. E plus E is again homotopy equivalent to M. So ultimately we can define this defines cohomology classes on M as well. This is again just the subspace. You want to think of this as morally the subspace of where two sections are dependent. Exercise perhaps, although I'll give it, is continue down. Interestingly, the way Stiefel-Whitney classes are best defined starts at the top with the Euler class and proceeds down, at least conceptually. And in our development with tome classes, that's a sort of natural order of things. Okay, let us stop the broadcast and see you next